Welcome back to the AutoML lecture series. In this part, we will talk about speed-up techniques for the performance estimation strategy in neural architecture search. So we talked about surrogate models in order to speed up the performance estimation strategy within neural architecture search. However, also these surrogate predictors involve at least partial training in order to evaluate the architectures and train our surrogate model, which can be still slow at scale. So therefore, we will talk in this part about two families of techniques to avoid this bottleneck. The first one is about learning curve extrapolation, where we predict the final accuracy from early training dynamics, as well as zero-cost proxies, which are a score of an untrained network, which is calculated using at most a single forward and backward pass. These predictors can also be embedded into the search loop to guide which candidates to evaluate next. The key questions we want to answer within this part is how can we reduce the cost of NAS to minutes instead of days, while still reliably identifying high-performing architectures. So we talked about performance estimation strategies in order to speed up the search strategies within a search space. Free speed-up families can be used for performance estimations in NAS, which we will talk about within this video. As already mentioned, the learning curve extrapolation, predict convergence from partial training, the zero-cost proxies, which are a score of untrained networks, and how can we actually use those for predictor-guided search to wrap predictors inside a search strategies for even faster evaluation. Learning curve extrapolation aims to predict the performance after partial training by extrapolating from the learning curve. So here we can see on the right-hand side an image using different parametric models to fit the observed learning curve. So we have our data, which is the black line. The network is trained 20 epochs, and from this information we want to extrapolate the information of how does my accuracy perform over the course of training using the given data, using different kinds of parametric models to fit the observed learning curve. So instead of training the network from scratch until convergence, we use a model to predict how the performance can be. On the other hand, we can use so-called zero-cost proxies. Zero-cost proxies are actually developed as part of performance predictor models in 2021. They run very fast computations, mostly a single forward and backward pass on a single mini-batch of data over a set of architectures to assign a score to each architecture. So the hope is that these scores are correlated with the resulting performance of an architecture after full training. So we calculate the score on an untrained network, and we want the score to be correlated with the performance after the training of the network. Therefore, important here, the zero-cost proxies are calculated on untrained networks. And we call them zero-cost since the score calculations is negligible small. So having only mostly one single forward and backward pass on 32 data points, for example. Some of these zero-cost proxies can also be data independent. So independent of what kind of data we input into our neural network, the zero-cost proxy will be the same for this particular network. For example, the amount of parameters. Here we will give an overview of different types of proxies exemplary. So we can use, for example, the number of parameters, where the intuition is that larger networks tend to perform better. They are data independent and mostly used as a baseline. The second proxy, which is used very widely in NAS, is SNP, which is just like the gradient magnitude at initialization, which reflects useful connections. So what happens if I get rid of one connections? How does my gradient change? These scores are data dependent and are in the area of pruning at initialization. So these are pruning based zero-cost proxies based on the fact that we check for useful connections by changing them, deleting those connections in order to evaluate their importance. The third proxy are grad norm, for example, which is just like the L2 norm of all gradients of one forward and backward parse. These are also data dependent, also calculated as being pruning at initialization. The fourth proxy is the so-called thin flow proxy, where the idea is to avoid the layer collapse. It is a product of all absolute values of the network parameters. So parameters of the network, the absolute values, and just like the product of those. This proxy is data independent since we just look at the network parameters and their values independent of a forward and backward pass. The next proxy is the so-called Naswood or Nwood proxy, which looks at the kernel matrix of activation. So it actually looks at what happens with the feature maps after the activations, saying the higher the diversity, the better the accuracy. This score is also data dependent and based on the Jacobian information of the neural network. And the last proxy are so-called graph, which includes topological information. So it only looks at the topology of the neural network, independent of the data, independent of the parameters, as well as the values, just the topological information, therefore being data independent and can be considered as a baseline. I refer to Krishna Kumar et al. From 2022 for an overview of more commonly used zero-cost proxies. The issues with zero-cost proxies are, however, that the correlation with the true accuracy is often weak. Simple baselines such as the number of parameters or flops are very competitive and very hard actually to beat. And since the proxies are evaluated on untrained networks, they may not capture all learning dynamics, which can behave and appear at different learning and different learning stages or deeper learning stages, and they can be also biased to larger models or wider channels. Another issue is that there is no single zero-cost proxy which consistently outperforms all others on all search spaces, so therefore they are rather unreliable. And most zero-cost proxies lack interpretability. However, zero-cost proxies can act as a fast screening step and discard clearly bad architectures, evaluating the rest more carefully. So using zero-cost proxies also in conjunction altogether, they can discard clearly bad architectures, and then the question is which of the rest we want to evaluate more carefully using different search approaches or performance estimation approaches, keeping in mind that the zero-cost proxies are not always interpretable. Having now talked about two different speed-up approaches, the question is how can we use those as well as performance in general, performance predictors in general, in the architecture search itself. So the goal in us is to efficiently find an architecture with the highest validation accuracy for the downstream task. And we can use performance predictors to improve the search efficiency. For example, we could use predictor-guided evolution. So the predictor predicts the score of the offsprings, which allows for the selections of the next candidates to be evaluated. We can therefore replace the expensive fitness evaluation with the predictor. So instead of training each architecture from scratch, we can use the predicted performance of the performance predictor. We can only therefore actually train the top K predicted architectures, updating the predictor as new ground truth evaluations become available, making the surrogate model more reliable, and therefore we can reduce the number of full training runs by a margin. Depart from predictor-guided evolution, we can also combine Bayesian optimization with the predictor. So using, for example, an ensemble of prediction methods to calculate the mean and uncertainty for candidate architectures, which was done, for example, in the work from White et al. In 2021 in so-called bananas. Here we can use the predictor as the surrogate model inside of Bayesian optimization. The acquisition function then queries the predictor to select the next architecture. And the uncertainty estimate comes from the predictor, which then guides the exploration versus exploitation. In summary, what we learned in this part is that we can use learning curve extrapolation, enabling early stopping of unpromising architectures and therefore reducing the training cost. Zero-cost proxies are a score which are calculated on untrained networks in negligible time, but are best used as coarse filters. And last, we talked about using performance predictors inside of search strategies, evolutionary methods, or Bayesian optimization, which dramatically reduces the number of full training runs needed. Thank you very much for listening, and I hope to see you in the next video.